Yeah, you can, I guess, just tell us, share to advance. Right, I think we can begin. So, hello everyone. Welcome to Privacy Enhancements and Assessments Research Group meeting. Yeah, your chairs, Shivan Saib, Chris Wood, and Sarah Dickinson. Welcome. This is the note well. Please do note this well in case this is your first IETF meeting, and even if it's not, please, it's always good to revise the note well. And also keep in mind the IETF guidelines for conduct as laid out in RFC 7154. Folks are expected to be courteous, have impersonal discussions. Keep in mind that we are trying to devise solutions for a variety of different needs and also be contributory and contribute to the ongoing work of this group and IRTF. We are currently looking for a note taker. So if someone would volunteer, that would be extremely helpful. We do need a note taker before we can begin. Thanks, Nick. Can anyone do the first part? Perfect. Thanks, Watson and Nick. Great, so we can begin. This is our agenda for our 1 hour long meeting, and a reminder that the session is recorded and the blue sheet attendance is auto-generated. Please keep video and audio off when you're not speaking or not recognized in the queue, and to enter the queue, there should be a join queue icon, which is kind of like a upraised hand. And I'll pause for a second in case folks have any concerns about the agenda or want to change it. And also just bear in mind that it's good to speak slowly in general, and I'll try to keep that in mind as well. And yeah, if there is no revisions to the agenda, Anton, you're up.
Yes, asking to share slides. Okay, so hello everyone. Welcome to my presentation. Today I'm willing to talk to the PRG attendants about some state-of-the-art artwork that I've been doing as part of my work. So my name is Antoine Fressancourt. I'm a research engineer in Huawei. And I'm going to put in perspective some work that has been presented in previous PRG session to protect privacy with some work in academia and see whether there is room for importing some ideas from academia in IRTF and then IETF possibly. Okay, so first, as a word of introduction, privacy protection has become a global consumer demand. It has been especially stressed by the fact that with COVID, we are doing increasingly important stuff online. Even people that are not tech savvy become accustomed to doing remote meeting, remote work, and exchange critical information over the internet. And people are becoming very wary of their privacy. So many web solution providers are addressing this need for privacy. For instance, Google has announced that it would drop support for third-party cookies, and build privacy sandboxes in Chrome. In the Worldwide Developer Conference in June 2021, Apple has made very strong statements with regards to privacy. Brave browser is catching up, even though its market share is still very small. Yet, even though many web browser providers are addressing privacy, people are coming up with ways to circumvent the privacy protections that they put in place. For instance, the pixel tracking technique that has been popularized lately is putting at risk privacy of consumers. So we think that to go further with privacy protection, we need to eliminate other identity linking identifiers and network layer identifiers such as IP are some of them. So if you look at privacy from a network perspective, privacy means the inability for a third-party observer to determine from the observation of a packet who is the source and who is the destination, and the inability for this observer to link source and destination for this packet. Depending on the attacker against which someone is willing to protect its privacy against, we may rely or not on third parties. For instance, ISPs tend to protect privacy of their consumers. Some ISPs are pushing some offerings, for instance, deploying VPNs to enhance the privacy of their customers. The privacy protection that you want to add depends on the strength of the attacker. Is it a very powerful attacker, script kiddie, someone with a lot of cryptographic computing power, someone who is stable in the network? And also, we need to address how is the risk that is associated with the communication that is protected. Sometimes the source even wants to protect against the destination in some specific context. For instance, some privacy in services, users may want to have access to those services without revealing too much about their private information. In general, since revelations made by Snowden, the state-of-the-art attacker against which we are trying to protect in network privacy is an attacker that is able to eavesdrop all the links and some nodes. Bearing in mind that protecting against a network consisting in only rogue nodes is impossible. So in the state of the art, the most powerful attacker is someone that is able to eavesdrop all the links and some nodes. So to protect privacy, if you look at state of the art, either from commercial solutions or from academic projects, you have two approaches to implement privacy. First, people that come from the internet as it stands and try to put layer on top of it to add privacy protection. This is the over-the-top approach that is on the left of the slide, and this is an approach that I call evolutionary. The main objective is to hide the source address of a packet or of a network flow from an observer using increasingly complex protection means. Those over-the-top approaches are mostly based on trusted third parties. Depending on the third party's willingness to protect the user's privacy, you protect against a strong or weak attacker. And those approaches can be deployed rather easily with an appropriate business case using an overlay approach. Some other approaches, mostly in the realm of academic solutions, adopt a built-in approach. Instead of trying to put some overlay on top of IP and work with IP, they resync the way network protocols should behave to protect the privacy of communications. So their main objective is to protect against a rather powerful attacker, as the state-of-the-art adversaries that I described in the slide before. Um, those approaches possibly try to avoid using a third party, to avoid placing too much trust in someone else. In fact, one thing that the academic research is trying to address is to reduce the amount of trust you put in someone else in order to protect your own privacy. Those projects are mainly future internet projects or academic research, but I think that they push some ideas that are worth investigating for implementers and people willing to develop deployable solution over the internet. So I will first go quickly through works that have been previously presented in PRG, mainly 3 projects. Google's Gnatcatcher that has been presented, I think, in IETF 110. It's a technology that is combining 2 approaches, two set of technologies, NearPassNet, that allows a group of users that are located in about the same location to send their traffic through the same privatizing server that is operating as a NearPassNet, and that this NearPassNet is effectively hiding the IP address from the site's host. And this NearPassNet is combined with willful IP blindness. In fact, in Gnatcatcher, Google has included the possibility for a website over legitimate purposes such as abuse prevention to de-anonymize the sender of a packet or of a network flow. Then the second solution that has gained lots of public traction recently, Apple's Private Relay. In Apple's Private Relay, you use a chain of true proxies to ensure source, destination, and linkability. Those proxies use a temporary public-private key pair that is provided by a private relay access token server. The private access token relies on the technologies that has been presented earlier, I think, in CFRG. And then the state-of-the-art of the project to which everybody compares is Tor. Tor is a very famous anonymity protection solution. It uses a circuits of Tor relays to anonymize TCP traffic. Tor consists in Tor uses Tor circuits consisting in 3 relays. Those 3 relays are the circuits are identified by a single identifier, and each relay removes a peel of the onion, meaning a layer of encryption, and after the 3rd relay, the traffic is sent in clear to the final destination it intended to be addressed to. Tor is renowned to be weak against traffic analysis attack, and some researchers have demonstrated collision attack when you control both the entry point and the egress point of the circuit. Then you can easily de-anonymize the sender of the TCP flow. Now I will present some academic research efforts. And I will start with a project called the Poseidon Lightweight Anonymity Protocol at Network Layer. So this project is the last of a series of lightweight anonymous protocols. Lightweight anonymous protocols were protocols that were designed in order to address some concerns with regards to available network privacy solutions without inheriting from heavy cryptographic constraints from mixed networks and other privacy-preserving messaging solutions. So in PHY, you use a helper node to build a low stretch path from a source node to a destination. The goal is to avoid an observer located on the path between the source and destination to be able to de-anonymize the source and destination. And this attacker in Phi is rather powerful because we assume that the attacker has a knowledge of the topology, so you need to hide the length of the IS path between source and destination and the position of the various ASs in this path. And payload encryption is bound to the path to avoid session hijacking attacks that have been done against previous lightweight anonymity protocols. So I will explain very quickly how Phi is working. So in Phi, you have a source S and a destination D. The source S wants to send a packet to D by using a helper node, help, the helper that is on the slide. So want to build a path going from AS6, AS3, AS1, AS2, AS5, AS9, so in red over the picture. To do that, first, S will send a packet to the helper. And in sending this packet, it will ask each AS on the path to place some information in a path segment vector. The path segment vector will contain information regarding for each AS, which was the ingress point, the egress point, the position of the information about the previous AS on the path, and a signature over this information. This path vector is built when the packet is sent from the source to the helper. And as you see in the vectors positioned here, you have a set of information. You still have some slots in the vectors that are not filled with information because this path vector is of a fixed size to prevent topological attacks. And you use and the helper will use public key encryption to reveal which is the final destination and use the path and start a back-off path construction method to build a path to the destination without having the ASs on the path from him to the source, knowing which is the destination. So you start a back-off process going from AS8 to AS1, and then in AS1, the path segment vector is stripped with information for AS4 and AS8 because they're not going to be used on the path, and then the path segment vector is built from AS1 to AS9. At the end of the process, S and D have built a path segment that is containing source routing information, anonymized source routing information that can be used to send packet between them. And another project from academia that is really worth mentioning is Sphinx. Sphinx is the major mixed network project. It's a project that was built in the realm of messaging systems. It consists in a chain of proxy server known as mixes, which take a message from multiple senders, shuffle them, and send them back in random order to a next mix node. And through the chain of mix node, you perform an anonymization procedure. Yes, Christopher? Okay.
I just want to we're running pretty short on time, so
okay, so I will go very quickly over this. So Sphinx is very interesting because it's very powerful. It has not been attacked yet. it's very consuming in terms of cryptography. But the very interesting part in there is that it uses a source routing approach to and cryptography to protect the anonymity of routing information. I will skip over this. While Sphinx is very angry in terms of cryptography, some projects like Hornet have tried to address and reduce the need for public cryptography in Sphinx in order to have better performance. One idea that is important and that I wanted to push in this presentation is that for now, many solutions that are being deployed rely on trust parties and use of relay nodes. And I think that in the community, we should look at projects from the academic realm and look at use of source routing concepts to address privacy issues. And this information, this presentation is a call to work on this alternative approach to build privacy at the network layer using source routing rather than trusted third party. So if you are willing to work on how those approaches could be translated and adapted in the current internet, I would be very happy to hear from you and to get your comments. Is there time for questions, or should we take them later on the list?
Oh, we can do questions. Ben, go ahead.
Yeah, time for questions. We'll keep it at these three.
Yeah.
So okay, somewhat cheeky, but why not just take your Sharpie and cross out application layer and write network layer and say that Tor is the network layer?
This is a very interesting approach. In fact, it has been investigated in an article called Tor instead of IP. And one problem with that is that Tor has some shortcomings with regard to some attacks with regard to anonymity. For instance, compared to Sphinx, Tor can reveal the kind of application that is running because it doesn't do pacing of the packets, and it's not immune against traffic analysis attacks. While some at the network layer, if you want to be immune against those attacks, you need to have some sort of padding and preventing someone to gain information by size of packet and size of the route. So
Tor,
if we
Tor
address those
does have
shortcomings,
substantial padding. I know that Tor does actually have essentially fixed block size. And quite a bit of padding in order to try to defeat these kinds of simpler attacks. But I guess I don't necessarily mean Tor precisely as it exists, right? The question is, you say at the network layer. What does that mean to you? And what's the importance of distinguishing between at the network layer and as an overlay like Tor?
For me, one aspect in the network layer is that you really want to have something that is very quick in executing from a cryptographic standpoint. So my aim to adapt the technologies that are used in the upper layer of the network layer would be to reduce as much as possible the use of public key cryptography, because it introduces delay and latency that is not compatible with requirements for applications that are not delay tolerant at the network layer.
Okay, thank you.
We have 1 minute. Can people be, we can go a little bit above, but folks wouldn't mind keeping questions extremely brief.
Watson Ladd, Cloudflare, a very quick question. It seems, and maybe I'm misunderstanding your presentation, that you're using the existing sort of AES relationships as the network, and you're picking a path through the AESs.
Yes.
This seems like requires a significant amount more work and traffic handling by AES that wouldn't be on the path anyway and would be now, and also would really, you're asking services that really haven't done a lot of work in the past to do a lot of computational work. Have you considered how this impacts deployability?
Just as a first comment, I don't want to claim attribution for the work I presented. It was just awareness. It's work that has been done by other people than me. So I'm just presenting here. I'm not the author of this work. But the way I understand your question and the addressing of the AS is that, sure, if we put privacy in the network layer, some routing the packets will take more efforts for transit net AS and transit equipment. But I think that this computing overhead is necessary if we want to provide privacy at the network layer, because if you don't have the aim of future work in ensuring privacy at the network layer would be to reduce this amount of computation overhead to ensure privacy. Is privacy coming at a cost? Yes, but the goal would be to reduce this cost as much as possible.
Jonathan Hoylens, Cloudflare. Have you categorized these pieces of work in the framework of DAS et al? Like, basically you try and say that there's a minimum. You have to either grow your traffic linearly in the number of messages, or you add latency in that's logarithmic in the number of users, before you can get any results as a sort of minimum proof. Like, there's a statistical proof that says you must have. So could you like, have you looked at each of those proposed things and said, oh, this one is adding minimum of bandwidth in the number of messages, or this one is adding linear bandwidth in the number of messages, and this one's adding logarithmic time, or whatever the trade-off between those is?
I think we started trying to do this categorization, not in terms of messages and overhead, but rather by trying to say, with a given protocol, what are the building blocks it uses to protect against this and this attacker, and trying to categorize them from a very analytical perspective. And as there are a lot of different technologies to protect against the same kind of attack by a given attacker, this fell short. Then we considered having a sort of scoring to categorize the level of protection the solution would provide, because it's fuzzier. But to say, okay, this protection is level 7, this one is 8, so it's a bit better. And with regard to volume of messages, overhead, etc., this comes to discussion on the mailing list yesterday about a graphs that I had in the slides before, and that was questioned. And I think we need, as a community, some more solid method to compare the solutions. And I threw back of the envelope guesses on the slide. It was my mistake. And I think that as a community, if we want to analyze those solutions more clearly, we need a more analytical framework. And I would be keen on working on that later with the community.
Thank you.
Hi, Antoine. David Skenazi, privacy enthusiast. Thanks for the presentation and for the kind of overview of a few various techniques. I just wanted to somewhat respond to your call to action. As someone who is working on deploying an IP blinding solution to protect user privacy, I care about this a lot. And To quote the great Inigo Montoya, I'm not sure that the word network layer means what you think it means. At the end of the day, where we do this in the network, you're saying source routing. I mean, Tor, private relay are all forms of source routing at the end of the day, because it's the client deciding how the circuit is built. And just doing it as a layer is not a real distinction. Saying that you're doing it at the IP layer, for this to have any kind of privacy properties, you're going to need encryption. So, you can use IPsec or whatever your favorite IP layer solution is, but all of them do the same thing. All of them start off with an asymmetric key exchange and then use symmetric keys per packet. So all of these distinctions that you've made through your presentations, I don't think they're correct. I would encourage you to look a bit closer as to how all these things are built, because I think you'll realize that having something, the layer at which is implemented, does not impact the security properties nor the performance properties at the end of the day. It's the choice of solution, the choice of number of hops, of which hops you trust, and things like that that matter. Thanks for looking into this, and thanks for bringing these new things, but I don't think in terms of call for action for the folks who are deploying this, I don't think these techniques are necessarily an improvement over what we have. All right, thank you.
Okay, thanks for your comment. I think that it comes back to the previous question with regards to the proper analytics and the comparison based on sugar.
Thanks a lot, Anton, for the presentation. We are running a little bit behind, so I'll go ahead and start with the next one. No worries at all. Thanks a lot for your presentation. I shall move on to the confidential computing presentation.
Yes, hello everyone. So we wanted to talk about confidential computing, a particular technique as applied to a particular problem, although it's also applicable to other similar problems. And the particular problem is DNS resolution. Go to the next slide, please. So why are we doing this? So we're sort of basically thinking around what can we do to further improve privacy, assuming that communications, encryption, and so on, it's largely handled. And we could use this for various kinds of things like infrastructure functions, such as DNS, but also for other stuff. And we want to go beyond. And just taking DNS as one example. So obviously today, mostly the domain name metadata is still visible on the wire, even with payload encryption of various actual data paths. But this will change as we get more DNS query encryption, we get more encryption of SNI options and so forth in TLS. But even when we get to the full encryption situation, resolvers still have the potential to see the user's entire browsing history, which is sort of an interesting data asset. And this also puts large resolver services as an attractive target for various kinds of pressures and attacks. And of course, there's been lots of work going on. I already mentioned all the protocol encryption aspects, but also there's been like this RFC 8932 came out of Deprive that talks about the practices that people are supposed to be doing when running some of these DNS or resolver services. Mozilla has their own requirements and so on. Next slide, please. So the context of this work, how do we build on all of that already exists, and what is the remaining problems, and is there a next step? And our general worry is that for many types of these like infrastructure services such as DNS, those services will become a major remaining source of leaks. Could be accidental leaks, could be attacks, could be commercial use, could be authorities requesting information from one or multiple parties. And if you look at this from a very high level perspective, then we need to protect users' data in flight, at rest, and in use. And so we've been running this little experiment with my colleague Jiri, who's also on the meeting, to see what could we do with confidential computing? Could we use it for this particular problem and get some experience? And we think there are some interesting opportunities and also challenges, so worth discussing. Next slide, please. So the basic idea here is that what if we run the resolver process inside a trusted execution environment, and we don't actually provide any user-specific data outside the encrypted process, even to the DNS operator, or even to the owner of the computer hardware or the cloud farm that it's running in, and sort of like a maybe a novel idea, run a service for the users and not collect personal data of the users. But we actually do think that there's some incentives for doing this, and damage from, if there is such, for not getting data about the users is not that big if you look at the details. We'll get to this in a bit. So basically this desired security property that we try to establish here is having the security perimeter around a service that prevents easy collection of information. This will not be perfect. We'll talk about some of the issues a bit later, but it should complicate the life of those who wish to collect data. Next slide, please. And I just wanted to provide like a very brief high-level introduction to trusted execution environments. I realized that on the audience, there's people who know far more about this than I do, so I'll keep it short. But basically, these trusted execution environments are sort of enclaves or environments where we can run code, and you can ensure that that code is not tampered with, and also any data that that code uses is not readable outside the environment and cannot be changed either. And of course, simply running something inside a safe environment is not enough. You have to also convince others somehow that you actually are doing this. And this we do through something called attestation. And basically, this is a process where a node can provide an assurance to outside parties, remote parties, that it's indeed running inside a particular type of trusted environment with specific configuration and specific software. This does require trusting at least one external party, for instance, the CPU manufacturer, because they can sort of vouch for their particular CPU and this particular key that the CPU is supposed to have, whether the signature is valid. We also need to understand what constitutes an acceptable piece of software that we should be running. So if you just run in a sort of secure environment, but don't care about the software that is being run, that's of course totally ridiculous, because as we know, software can do anything. And so basically, if you don't check, then you don't care what actually happens. But you can do this kind of a check, what software is running, what software image hash is being run. This technology is pretty heterogeneous or developing at this stage, but there are multiple building blocks at IETF and outside, and it keeps evolving. Next slide, please. So the basic setup that we did in our experiment was that clients query DNS information from a resolver, and they do this query through encrypted query protocols such as DO or DOT. And then this encryption ends up inside the trusted execution environment, and the encryption is terminated there. And all the information about what is this particular client asking about, what name is being resolved, stays inside the TEE. So not even the operator of the DNS server or the cloud platform can see what's actually being asked. Only the client knows about that. And then this code, this particular piece of software inside the TE knows about it, but it doesn't leak that information. Of course, you can't do, like for most problems, DNS is very similar. You can't do it sort of entirely on your own. You have to sometimes ask other people some other information. In this case, if you don't have cache hit, then you have to go somewhere else. So there is an interaction with outside world. There's some danger that an observer would be looking at this system from outside and see that, no, the client sent a query, and oops, now there's another query sent right after that to this server, and that server seems to be, providing an answer about example.com, and therefore probably this client was asking about that. You can't entirely prevent finding some information about this, but you can make it a little bit more difficult. For instance, in our case, since you do have caching, you can only do that in some cases. And then we, for instance, in our system, we implemented timing obfuscation and some random background traffic that confuses people about, or outside observers, what's actually going on, what queries relate to what. Next slide, please. So that's the basic setup. And now we can talk about some of the considerations that we sort of found out in our analysis of trying to do this. There's some upsides and then some downsides and some other conclusions. So the upside clearly is that we were able to hide all user-related information, and we actually argue that this is something that we should generally strive to do if we can. It's a very useful thing to do. That's not the case that we should always leak all information that we get to some data storage that then can be used against the users. That's bad. We should try to limit the information that's actually leaked out of these processes and do it in a technical manner that we can actually trust that protection somehow. And that relates to the other upside, that it's not just we trust a particular company, that they're a good company, they can do this well, I trust them. But we could actually get some evidence of their compliance to that practice, trust but verify model. And then I mentioned the incentives earlier. So one potential incentive to do this is that you could advertise this, that our service doesn't actually leak your information with users' browsing history, but it actually keeps it private, and we can actually show that we're doing this. And so that I think would be a significant advantage in marketing a service. The other thing is that you might consider lack of data from users' actions a downside, but you could also see this in a more positive light, that if you don't do that, then that's actually the way it should be, but you can still get some valuable data. This kind of reminds me of the book yesterday. Earg and others were talking about Priv and how you can provide some aggregations of statistics rather than per user relevant information. It's a very similar situation here, that you could provide, perhaps using some of the Priv techniques, you could provide some aggregate information, that what is the most popular name, and so on. You can also perform more complicated tasks, like if you need to do some geolocation or whatever special thing, as long as you do it inside this trusted environment where no information leaks outside from, then you can basically still do a lot of useful services for the end user, even get some information that's relevant for your business, but not leak the actual end user's private data. Next slide, please. A potential downside is that in addition to this data collection, there's some other operational practices or operational impacts that get changed. So, what about scaling? What about monitoring your systems? What about debugging? What about DDoS attacks? And these are actually difficult questions. I don't claim that we have clear answers to all of this, but we did find that you can have some ways to address this. So for instance, you can do some reporting that is at the level of these aggregate statistics, that how loaded is this instance? Where are what is the top 2 biggest sources of questions sent to this server? What is the top 2 questions or top 10 questions sent to this? And from those kinds of things, you could determine a lot of things, both about scaling and errors and possible attacks that are ongoing. A pretty hard downside is perhaps dependencies. You'll be dependent on a particular hardware. Not all CPUs can do this. So we were building some of these prototypes. I realized that some of the computers that I have in my basement can do this, but others cannot. So I was maybe too cheap when I bought the CPUs, but so it does require some particular hardware or newest CPUs. You'll be dependent also on these manufacturers for verifying that this is indeed their CPU. You might be dependent on somebody who can actually check the software that this is like a reasonable piece of software, and we looked at the source code, we were able to compile it and get the same hash, and it doesn't leak information. It could be a significant effort, but maybe there are organizations in the world that could be looking at this. I don't know, EFF or something like that, or Let's Encrypt, or could even provide such software. Performance, a common question, and here, like the performance impact does vary, and maybe there's other people on the audience that know more actually, but we found that this typically is an impact, but it can also be fairly small. One other set of people who've done this in our draft, there's a reference to PDOT, which who did a very similar thing to an existing open source implementation, and found out that at least in some situations they were able to get the same or even better performance in the way that they were using it. But maybe that's a bit of a special case. I like to think of this generally today with the technology that's available right now in the CPUs. Typically have to do like a context switch between the trusted and untrusted parts of the system, and so basically for everything that you do, you add an extra context switch, and that's not the only way to do things, and you don't have to do like context switch for every little step that you do in the system, but it can have an impact. So getting twice the, or having to burn twice as much time or half the performance is a possible outcome in some configurations, for instance. But it can also be negligible. Next slide, please. So basically, this is not a cure for all problems. Obviously, there's lots of attacks that one can think of. You all know about various CPU problems and so on. But it is an additional hurdle that you can get through. Many kinds of security technologies. This is just yet another one, but it's a pretty big hurdle to go through if you're sort of an agency that tries to get data. So we think it was useful, at least the way that we saw it. We also think this is orthogonal to many other techniques. I think we're out of time, so I don't want to read too much of it. Just go to the next slide. That's the last one. Conclusions. Oh yeah, one more. So there's obviously areas with active development. The hardware is actually developing. We expect that future generations of hardware actually have much less performance impact, for instance. There's obviously more research needed on operational impacts and some other aspects of what's the best model and deployment setup for attestation. Next slide. So conclusion. So the main conclusion is that we should really pay much more attention to the data that's held by servers and think about how can we reduce that data in various ways, and how can we protect that data like we do in this particular work. We think it's crucial. Maybe this technology is not like prime time for super wide deployment, but we think it's ready for some deployments. It's clearly used by a lot of systems out there today, yeah, we think it's interesting, even though it does have some interesting problems as well. Be happy to hear people's thoughts on this, whether you think it's science fiction or potentially feasible, or whether some things need to be taken into account. Thank you.
We really only have time for only a couple of questions. So Ben, again, wouldn't mind being really brief.
So I think this stuff is very interesting. I don't know how far we are from being able to use it. My question was just, did you use something like oblivious RAM or path ORAM?
I lost you there for a bit, but I'm not aware of that particular technique. We used for our particular system, we used Intel SGX, and which has
right. So in general, if your SGX encrypts all the contents of memory, but a local adversary can still observe all the memory access patterns. So that actually makes it relatively easy to identify which DNS queries are being performed. You can see each query hit the right spot in RAM where that data is stored.
Right. Yep. That's one of the attacks.
I was just wondering,
Daniel?
yeah, I was wondering, do you have this up where somebody can query it? What's the performance look like? And do you think that this would preclude any of the other DNS privacy work that's being done at the IETF?
No, I think this is definitely sort of complementary. So if you do this, it doesn't mean that you don't need to do encryption or oblivious or any of the other things. It just means that for the particular function that you're doing, you're protecting it better from outside influence. And of course, if you open up the computer and look inside the CPU and have probes and everything, you can find some information that you could even see inside the CPU what's going on, even if you encrypt everything that comes out of the CPU. And we don't currently have this up, but we've been sort of thinking about the hackathon project where we could do some testing. So we basically do the standard protocols, so we could easily do some testing. It's not currently open source, our particular prototype. And Earg?
All right, thanks for presenting this. I mean, so like, I think, there was like a lot of enthusiasm about 5 years ago for enclaves as sort of a replacement for multi-party computation and things like that. But the bad news is it doesn't work. And like, I can just point you to like a lot of papers of like people breaking the SGX, like from basically from just like programs running on the machine. You don't even need an electron microscope. Daniel Gang has done quite a bit of work on this. And like, it's not just like extract the data, it's like extract the keys and then go sign your own stuff. So like this generation of T simply is not up to the challenge. And this really goes to the threat model, which is that the threat model here that like many things were designed for was like, I have like a phone in my hand and they want me to stop probably from like stealing, like videos. But the situation in this case is quite different, which is that this is like running the data center of someone who's by definition extraordinarily sophisticated because they're able to run like a very high production service. And so like to have the threat model be that those same people like can't like call Daniel Genkin and learn how to extract the keys for SGX like seems pretty implausible. So I think like until we get to the point where like it's actually quite hard to break these enclaves, I'm not quite sure how this works.
Yeah, I think, there's no debate that there are no attacks. There clearly are attacks, lots of them. But I think this is still a barrier for people to do. But I'm not basically disagreeing with you because we also are waiting for the next generation. So.
Yeah, I guess as I think it had to be the case that like you needed like I think in order for this to be plausible, it had to be the case you had at least decapitate the chip in order to get the keys. Because I guess the standard is like basically there's software attacks. It's just hard to understand why like any cheating resolver isn't going to do it.
Okay, I think we should move on to the final presentation. Thanks, Yari, for that. And Matthew's up next for an update to the IP address privacy considerations draft. And do you want to, Matthew, you can just control, you should be able to, wait, actually, sorry. You should be able to use the preloaded slides, unless,
oh, yeah,
share your screen.
That's fine.
Okay.
Let's see. All right. Sorry, Siobhan, should I load my slides?
Yeah, you can either ask for preloaded slides or you can just, I guess, request permission.
Preload slides are fine.
Okay. I think you can ask for that permission. There's a shared preloaded slides. Yeah, there we go. This is fine. You can just share your screen.
Okay. Okay. That's good. All right. Hi, everyone. I'm Matt Finkel. I work at Tor. And recently we started working on a draft around IP privacy considerations, specifically what what do we have to take into account as we develop and deploy and adopt IP privacy within applications. We recently published an updated draft. I encourage everyone to go look at it. All right, so where did this come from? This came from, or as a result of the IP privacy interim that took place earlier this year. And coming out of that, there was a question about, how IP addresses are used and why IP privacy is such a controversial and difficult topic in a lot of spaces. And IP reputation is a significant use case. And so the draft itself started out by looking at how to create a new reputation system that could replace IP privacy. And admittedly, this was ambitious. And we'll actually get back to that because it's actually not even one of the most important aspects of how IP addresses are used. And so we're taking a step back, and the draft now takes more of a holistic view of IP addresses and how they're used. And we're basically looking to categorize the different use cases and the different signals that platforms and providers are currently need or currently are using for IP addresses. And then we're looking at sketching some replacement signals for those IP addresses. And this is obviously an iterative process. And with that, we're just having conversations with people from all sides. So obviously, coming from the Tor side, we only really see one aspect of this. So we've been having some very fruitful conversations with platforms and other companies and other providers. And so the draft itself is very much a work in progress. Within this draft, we added a lot of new use cases, primarily around anti-abuse and various GeoIP use cases. There's also a new description of various IP address use cases and restrictions within legislation worldwide, which is captured. And then we have some replacement signals, and we also started documenting categories of interaction, which provide an interesting motivation for some of the signals. And again, we started getting rid of the reputation system just because it's more of a distraction right now. And then in terms of next steps, we're continuing to talk to different parties. The draft itself is very heavy on anti-abuse, and we don't capture a lot of the other use cases of IP addresses. And so we're going to look for other people who are interested in talking about how they use IP addresses and what blockers they see for accepting clients over IP privacy or over private IP connections. And through that, we're going to iterate on signals, and the draft itself is becoming quite long and complicated. So we'll probably look at refactoring and making it easier to comprehend. And we're also going to look at and continue to be involved with other groups within the IETF and W3C and then various standards working groups. There's recently an anti-fraud community group launched at the W3C that we're interested to see what comes out of that. And then in terms of open questions and issues, obviously going back to refactoring, just like what is the scope of this draft and what should be included for within the purview of Earg and just what's generally useful. As an example of open issues, there's a question of mandatory signals. This is obviously very contentious because we're trying to get away from mandatory signals with passive semi-stable IP addresses. But on the other hand, malicious behavior and just general bad actors take advantage of not having a mechanism to re-identify them. So that's and then they're just general GitHub issues, which go into some of those issues and others. And that's my update. So happy to take any questions or comments.
Yeah, I think we don't have any time, unfortunately, for questions.
Well then, okay.
Thank you, Matt, for all your work on this draft as well as the others. Based on the sort of interim meeting that we had a while back and previous updates in this draft, I think we're likely going to seek adoption by the group. So if folks here have not read it, we would encourage you to read it. And we should be following up on the list soon-ish to start an adoption call. I don't know, Siobhan, if you wanted to add anything more.
Nope, that's it.
Okay, great.
That sounds great.
All right, folks. Thanks for your time. And we'll see you on the list.
Thanks all. And thanks to our note takers, Nick and Watson.
Yes, thank
Bye-bye.
you.